Thermal stress has now become a very important topic in structural mechanics. It used to be a specialty topic and studied only by a few people who perhaps took an entire course on the topic and had a separate textbook for it. Now, however, thermal stress is becoming very common. There's a great need for information on the topic through the increased performance of vehicles, engines, catalytic converters. There are many devices now, both in commercial and military applications, that are high temperature. Luckily, the technology has kept pace, and we find that we can study thermal stress in one lecture in finite elements. We find that the technology is really ready to accept an analogy of thermal stress where the temperature field's converted to an equivalent nodal load as if it were a body force. And then the equations that we've already developed handle that quite well. Even the sign convention comes out easy to understand. So I'm pretty enthusiastic about the thermal stress area as a reasonable technical topic, and I think the average engineer viewing these lectures should be encouraged to try it when it's needed. It's not difficult. The commercial codes almost all will incorporate thermal stress concepts, and I'm pretty certain they'll all be based on this same idea of converting to an equivalent nodal load through the artifice of a pre-strain. In this lecture, I will do some basic discussions on thermal stress. We will use the rod as an example to carry out these ideas, showing how a rod can expand when heated, and then the strains that appear and the equivalent nodal loads, and I'll carry out a little numerical example. I did once a problem in a fusion reactor where there was an impulse of energy that created a temperature field and an instantaneous stress field that led to motion of some molten lithium salts. Some comments that I add have to do with the practical application in finite elements, and then we're going to do some problems in both 1 and 2 dimensions. Temperature fields really have 2 major effects on structures. The first is the one that we talked about, where you get a mechanical expansion and then the creation of mechanical loads. The second is the effect on material properties. I list those 2 things here, and of course we're going to concentrate on the mechanical expansion part of the problem. The change in materials properties is really different and often is handled by table lookups, where the computer program will check the temperature and then adjust the material properties. It's interesting that mechanical expansion effects due to temperature are considered a load, so the application of a temperature field is often covered in the loading section of a computer code. Well, these high temperature changes that cause this temperature field occur in high-speed flight, in engines, particularly the high temperature engines that are now becoming more and more popular. The military, for instance, would like an adiabatic engine, which is ceramic if possible, and for efficiency, the higher the absolute temperature, the more efficient the conventional internal combustion engine is. Catalytic converters are getting hotter. We tell about a story in Ann Arbor where a gentleman bought a new Cadillac and a day or 2 later went to a football game and parked his Cadillac nicely along the curb, not noticing there was a pile of leaves that he had parked over. Half an hour later, while he was cheering at the game, his car burned up. And I can imagine his reaction to that football Saturday was a little different than usual, but it was a total loss. We can, in principle, treat the thermal field in our mechanical expansion problem either as an initial strain or as an initial stress. But in practice, it's turned out we use initial strain as a major approach. When we use initial strain as our approach, then we can simplify the stress-strain law. and we get this form. Now, we showed earlier the effect of both prestress and prestrain. The effect of prestrain is given here, and it can be converted to an equivalent nodal load, which is a mechanical load. Therefore, if we can identify what the prestrain would be caused by thermal expansion, we would be able to use this equivalent nodal load analogy. The strain in a rod element, which is a one-dimensional element, would be the linear coefficient of expansion times the change in temperature. In principle, that could be a function of length along the axis of the rod. The sign convention for thermal strain is simple because we take it to be positive when the thermal strain is expansion, and then we take it negative when the thermal strain is contraction. And that corresponds then with almost all materials to a positive temperature causing a positive strain and a negative temperature causing negative strain. Here I sketch a rod with a high temperature at one end and then a low temperature at the other end. And then that will lead locally to positive strains, and then if this is cooled over here, it'll be negative strains. So it's easy to track what we mean by thermal strain. And we consider what it is when it's free to expand locally. So there's no complication at this level about whether the body is constrained and whether it can expand or not. You just consider locally what is the tendency of the body. Would it like to expand or not? It's a point-wise quantity. Now, though, if you go the next step and ask about thermal stress, then you're caught in a global problem, and the stress will depend on the boundary conditions. For instance, take this rod at the lower left that's free at one end and clamped at the other. If you heat it in the middle, there will be substantial thermal strain, particularly in this heated area. But it's free to expand, and there will be no stress anywhere in the body. So the equivalent nodal loads that we're going to develop will cause that hot area to expand through a set of loads at the end. It will turn out at the ends of that heated region, but the body will freely adjust to that. In contrast, if you had a captured rod shown here in the middle and you heated the center area, then you would get the thermal expansion in the center, but then you would be captured at the ends so that there would be developed some mechanical strain in addition, and the sum of those will cause a constant stress from end to end on that particular rod, just because it's such a simple case. A third example is this sheet metal that's been heated in the interior by a blowtorch, say, and wants to expand. Now, in this case, the material in the middle, although it would like to freely expand, will be mechanically constrained, and so that the red area will be under compression, and typically the outer region, which is cool, will be under tension. You can argue that by taking a cross-sectional cut through here at any cross-section and just realizing that if the center hot area is trying to expand, then it's going to be putting force on the cooler areas and making them actually be in tension. So you've got this kind of a force balance. I'd like to make a short excursion into a practical rod problem to illustrate the effect of the temperature field on the various elastic laws. This isn't going to be a full-blown example, it's just a one-figure demonstration of something. We have here a rod, a single rod element pinned at the left end and with a live load on the right. It's free to move on the right end. When I discuss any system, I like to show the three figures shown below. The first one is a total system behavior of one of the live loads, let's say, versus one of the coordinate displacements. And we've used F2 and U2. The middle one is the strain and stress relation, a generalized Hooke's law. And the third one is the strain to nodal displacement law. Why don't I start with the right one first and give you what might be an amazing claim, namely that the thermal effect and the mechanical effect is the same in regard to measuring a total strain versus nodal displacements. In other words, strain has a definition that's purely geometric. It has to do with the motion of particles and the relative extension and distortion caused by motion of nearby particles. That doesn't depend on whether that displacement was caused by a temperature field or a mechanical load. And therefore, those two curves are identical. Now, a thermal load can make you move up and down on this curve, as can a mechanical load. But if you call this total strain, then those two effects or those two lines of action are coincident. When you come to the stress-strain law, however, and this strain is viewed as a total strain, you find that the loads or the stresses are lowered by warming the body up, because then the body tends to expand without truly a corresponding amount of tension required or mechanical load required, and so the curve shifts in this direction. Thirdly, there in the system law, you find that that's a reflection of the two curves to the right. Both the geometric and the material law feed into the total system behavior, and again you get a shift here, which is due to the material law and the artificial inclusion of the temperature as a pre-strain. Now let's look at some specific cases of this thermal strain. If we look at a three-dimensional solid, for instance, shown in the material coordinate system to the right, then we need possibly for orthotropic material 3 separate coefficients of linear expansion. Now, of course, the temperature at a point will be independent of direction, so you'll have a common temperature. This would then create a set of thermal strains. Now, it will turn out that in principal material coordinates you get no thermal shearing strain. So the body tends to expand in a nice way such that a cube initially might turn into a rectangular prism, but there won't be any shearing motion. For a plane stress problem, we have a similar result, namely that an orthotropic material would again have different linear expansion coefficients in the different directions, and there would be no thermal shearing strain. In plane strain, there's just a bit of a different relation. If we have plane strain, we mean that the body is captured at the ends. In other words, there's no strain in the z coordinate direction. But as you heat the body, it would like to expand in all 3 directions. It cannot, and so the axial expansion, you might say, spills over, which is a Poisson ratio effect, into the lateral dimensions. That effectively enhances the expansion, and rather than a unit value here, you get 1 plus nu contributing to the expansion in the 2 lateral directions, still allowing orthotropic materials if need be, but still with no thermal shearing strain. So far we've used material coordinates, and you might ask, why do you have to do that? Here I show the relation in the case that in plane stress you decided to use some general coordinate system. And unfortunately now, you will get a thermally caused shear strain. So that complicates the problem a little. But the real problem is that it would be very hard to measure these linear expansion coefficients in other than a material coordinate system. It's time to do a numerical example just to get some intuition for the problem. We'll start with a rod element. I'm going to do this example in an unusual way, namely that I'm going to develop the equations for the system first without putting boundary conditions on. That lets us look at some of the basic relations and get some ideas about the equivalent nodal loads due to the thermal field, which are really not dependent on boundary conditions. Then later we'll go into a free expansion and a fully constrained case that will show some of the mechanical details. So we'll start out here with this picture of a two-noded rod element, constant area. We're going to assume that it's been heated 100 degrees, and we have material properties for aluminum given here with the expansion coefficient. The rod is 100 millimeters long, 1,000 millimeters squared in cross-section. So it's a typical little aluminum link that you might imagine you could hold in your hand and then heat to 100 degrees. I guess the heat of your hand wouldn't do that. That's the difference between freezing and boiling, so it really would be quite a temperature rise. So let's look at our general laws prior to establishing any boundary conditions. The stress-strain law, or the material law, now would include this thermal expansion term. It was a positive temperature that we imposed, and the aluminum will try to expand, so we're going to get a positive thermal expansion. And that's shown here, where I've incorporated the alpha and then the delta temperature. Those two numbers then come out in order of magnitude 10 to the minus 3, but ultimately that pre-strain is going to be multiplied times the Young's modulus, so it will become a sizable number. We'll see that in a second. The equations of equilibrium for the system prior to putting boundary conditions on involve the conventional stiffness matrix, the nodal coordinates, the true mechanical discrete loads, and then this set of equivalent nodal loads due to our pre-strain. The most important thing for you to see in this problem that we're working on is the value of the equivalent nodal load at each end of the rod, and we get that here. Here's our general expression for equivalent nodal loads. It's a volumetric integral over the strain and the material property and the geometric property, so it involves all aspects of the problem. When we put our specific case in here where we have an alpha delta t for a rod, then we have to have the Young's modulus for the material property, and the strain matrix, which is a constant in our case because this is a constant strain element, is shown. Then as we multiply that out, we get a 2 vector, and then putting in our specific numbers that we just developed, we get 150,000 Newton forces right and left on that line element shown below. I think this is really important. Here you see that we've converted a 100-degree temperature rise into mechanical forces of 150,000 newtons that are trying to stretch that rod. Now the stretch in the rod is going to be the same whether you had the temperature field or whether you have these mechanical loads. And so we can convert completely to a mechanical problem then by this artificial modeling of the temperature field as a mechanical load. I'd like to assemble the system equations as far as possible prior to applying boundary conditions. So that's done here. and we've embedded the equivalent nodal loads in the proper position. We've got the mechanical stiffness of the system here, and so what we need to yet specify are the boundary conditions in some combination on the nodal loads and nodal displacements. And I do summarize here that these mechanical loads are going to cause the same expansion as the heat would have. Our system behavior will be shifted as shown in this lower diagram, however. Now let's put some specific boundary conditions on our system of equations. If we take the case of this rod and it's unloaded on the right end with zero force and the left end is pinned, then we can put those conditions into our previously assembled set of equations. So the zero force on the right gives a zero here, the zero displacement on the left gives a zero here. And we can find the displacement from the second equation, which comes out to be 0.22 millimeters. And now we have fully solved a boundary value problem where, in this case, the loading was entirely thermal loading. I show some of the system behavior below. If we go into the stress-strain curve first, since that's the local behavior, we would find that we started with an unloaded, undeflected system at state 1. We then heated the body, which I'm going to represent with a state 1 prime as a system with thermal load on it, but not the full mechanical set of loads. Now we stop at this point in this boundary value problem because we don't add further mechanical loads. Had we done that, we would have moved up and down this red line though. And the system behavior on the left really mirrors what happens down at the material level, where again we move horizontally from state 1 to state 1 prime. Let's do a second boundary value problem, and this is the fully constrained case. Here I'm going to have the displacements at both ends of this rod to be 0. Meanwhile, we heat it 100 degrees. In this case, I've got both the zeros shown on the right-hand side, and the goal is to find the reactions. That's just a forward multiplication, although even that is trivial because you get zeros on the right-hand side. So you find then that the forces are just the negatives of these thermal loads. And so the reaction forces then are facing inward as shown, and of course they exactly balance the thermal loads. So in this case you see where the thermal load causes mechanical loads. In this case they're loads of reaction. Now let's look at the system behavior and the material behavior under this combined mechanical and thermal loading. We'll look at the material law first on the right. Now what really happens is that you move directly from your state 1 to your state 2 down below on the red curve, because as you heat the body, you simultaneously incur the end reactions that directly oppose the thermal load. But it might be instructive to do a mental experiment where we first break the boundary conditions, let the body freely expand as we did in our earlier problem, move it to this point 1 prime now, which is just a mythical point. Then by reimposing the boundary conditions, you'd have to grab the rod and scrunch it back to its initial position, which would move you down on this line and would require mechanical loads moving in that direction, ultimately to end up at this state 2. The interesting thing is there's no mechanical strain at state 2. And Maybe that's physically difficult to comprehend, but think about that a minute, because you see the particles in the body have never moved under the combined loading. They're in the same position as the initial state. And then the system behavior on the left would just show the same behavior as this material law. If you do the complete problem, and you find this out in the major finite element codes, that if you ask for stresses or stress recovery, you'll find then that you're going to bring the temperature field back into the problem a second time. And I point this out as kind of a footnote here, because it hadn't dawned on me either, I must say, for some time that that would be done. That we used an equation at the outset to eliminate temperature completely in terms of mechanical effects, and it disappeared from the problem. But later on, if you want to recover stress at an element level, you've got to bring that temperature field back in again through the stress-strain law to get the stresses. So temperature will rear its ugly head a second time in the total process. I'd like to present a small case study just to show a problem where there was some thermal loading. I once worked on a fusion reactor proposed by KMS Fusion in Ann Arbor. This company got ahead of the world literally in pellet fusion. It's sometimes called inertial confinement. Laser light shines on a small pellet of deuterium and tritium and causes it to implode in a way that it reaches a critical temperature and pressure, and then the material will fuse. It's like having a small sun, and I've drawn a sketch of such a reactor down below where the pellet goes off, and hopefully the walls of this reactor, which is 10 meters in diameter, could be protected by these falling curtains of molten lithium salts. The lithium plays a double role in that you can also breed more tritium in this way. There are competing ideas. There's the tokamak reactor, very important in Russia and at Princeton University, magnetic confinement, and then there are some hybrid methods where they combine some of these features. The object of constructing such a fusion reactor was ultimately to capture energy, either in the form of electricity or chemical energy, and then essentially exploit the tremendous energy available in the fusion process. Now, the fusion creates fast neutrons, and you have to absorb those in one way or another to capture that energy. A lot of the energy is ultimately released as thermal energy, and most of these nuclear reactors have to do that. They've got to convert nuclear energy to thermal energy at some point. For us, the key to absorption would be in those molten metal salt layers, and when the fusion goes off, then you'd have this falling layer of molten salt here. The true temperature rise, as it was measured, had a profile shown here, and it occurs essentially instantaneously in terms of the reaction of any mechanical object. Now, it isn't quite instantaneous, but the neutrons travel at some moderate fraction of the speed of light, and they get absorbed in a centimeter or two at the first encounter with an absorbing material. Now, I decided, just for numerical purposes, to approximate that slightly non-uniform temperature field by this uniform one, more or less as a step function in temperature, that would be applied to my layer of molten material at an instant of time. At the time I did this problem, I was using the SAP codes, and the SAP codes didn't have the capability for temperatures that changed in time and dynamics at the same time. They could do transient problems of uncoupled nature, but not the coupled temperature and mechanical problem. And so I decided to do the mechanical analogy myself. So this was kind of a homemade modeling trick done within the SAP code. What I did was go completely to a mechanical model, and I had the properties for this molten lithium salt, and I set up 10 elements, and I decided I would start them as if they were instantly hot on these 5 elements, and then see what would happen in terms of waves and stresses and so on. When you calculate the equivalent nodal loads, given the bulk modulus for that lithium salt, I came up with some forces that would be applied to each little element. The interesting thing you see is that you get this cancellation at the boundaries of the elements. And the net result when you assemble the equivalent nodal loads is this picture shown below, where that entire temperature profile is replaced by 2 mechanical loads, one of them here at the center and one at the left end. And then this became a mechanical wave propagation problem. One of the first things I found was I could follow the motion of this rightmost disturbance here as it moved through the elements, and I got the speed of sound in the lithium salt within 1%. Secondly, though, I found that when the waves reflected at the end, as expected, you get a tensile force. And in a linear theory, typically you'll get the same tension reflected as you had compression on the ingoing wave. Well, I could use that to get some impression of whether the material would spall off, what it would it do, and of course it did. I mean, it's related to cavitation and so on. If you exceed tensile forces that are greater than the surface tension capability of the material of this fluid, then it will just fly off. I think this was mostly a demonstration. We were interested in patenting ideas, and I think the technology was a little simpler then. But it certainly is an example of exactly what we've talked about to this point, namely a temperature field in rod-like elements and then following what happens. In this case, we got transient motion, which is beyond our interest this term, but nevertheless covered all of the mechanical effects of that equivalent nodal load pattern due to temperature. So far we've worked with one-dimensional problems. I won't skip 2 dimensions, however, because in the problem session we'll work through a triangular element that has a temperature field, and you'll see the thermal loads that result. Now let me give 3 comments that come from practical finite element usage. First of all, you can specify temperature in most codes either at the element level or the node level. You have to be careful because there is some minor difference around the edges of your temperature field. If, for instance, you had a problem shown at the bottom here as 6 rod elements, and 3 of them were hot and 3 were cold, as in my case study, then if you specify temperatures in the elements, you will indeed get an imposed temperature field shown in this sketch, where the elements will all have the proper temperature. If, however, you specify temperature at the nodes and give these 4 nodes as hot, you will find that typical finite element codes will average the temperatures at the edges of the elements, and therefore you'll get a lukewarm element here that originally might have been intended to be cold, because it will average between the hot and the cold regions. I think that's not an important modeling idea, but it surprised me when I saw that there was a difference. My second comment has to do with mesh generation. There really are some serious problems about how to mesh a problem that has both mechanical and thermal loading. I've given a really tough case below here as an example, especially if this were to be modeled with plane stress elements, let's say, so that there would be some rather fine mesh laid out through here. Maybe you would want to capture some of the stress concentrations at the boundaries. Maybe you'd want to capture some of the stress concentrations, if any, near these rapidly changing loads. I've got the mechanical load pattern here, and then I've got the hot spot for the thermal load. Now, the underlying law really for all meshing in these mechanical systems, since we deal with a mechanical equivalent, is that you've got to have fine mesh where you have high stress gradient. And I mean stress gradient. Now, I've shown here cases where you have high load gradients, and we have high temperature gradients at the ends of this hot spot. We know that the temperature gradient converts into high strain gradients, at least in terms of the equivalent thermal strain. So when it really comes down to it, it turns out there's no general theory yet. And I've only seen one textbook comment on this topic, and they also have been caught in a quandary as to what to say and have hedged. It appears that at present you need to do moderately fine mesh anywhere that you're in trouble, whether it's the mechanical problem or the thermal problem. And just do the best that you can, and I would hope that with a certain amount of product knowledge, once you've solved a problem or two, you'll locate where the high stress gradients are and concentrate your attention there. A third comment has to do with the use of temperature loading to establish pre-stress in bolts. Of course, this is actually a mechanical interference problem where you've established an interference by over-torquing the bolt and then pre-straining the bolt. But what's often done is to build a model, as shown here, of a relatively rigid joint and then a relatively flexible bolt, and the assembly is made initially in mechanical contact but no mechanical pre-stress. Then the pretension in the bolt is put in by cooling the bolt a certain number of degrees. Generally, the engineer will make an estimate of the cooling that would be required to stress that bolt to its proper value, which might be 90% of yield or some other corporate criterion. When you do the cooling of the bolt and you solve the total system problem, you invariably find that you don't get as much tension in the bolt as you had hoped. Why? Because the joint itself will relax a little bit under that tension and will relieve some of the previously applied pre-strain. So it usually takes a second run to get the proper tension in the bolt. But usually 2 runs will do it. In a linear system, you should be able to make that change and hit the exact tension on your second run by ratio and proportion. Problem 1 in our problem session is a rod that's captured between 2 rigid walls. It's then heated on its left half and cooled on the right half. Our question is to find what is the stress in the rod. We also en route will find the displacement field, and I would anticipate that that center node would move to the right. I'm actually going to model this with 2 separate rod elements, each 100 millimeters long. The area is 1,000 millimeters, so this is the same sized rod as we used in an earlier example. But I've chosen different material properties. I have a Young's modulus, I have coefficient of linear expansion, and here I put in this heat conduction coefficient. Why is that there? Well, that's just a little bit of a red herring to make people sure that they know what they're doing. And I find on exams that it sometimes really strikes terror in people's heart to have extraneous information. But heat conduction won't have anything to do with this problem if we've been given the temperature field a priori. The solution will be done with 2 rod elements, and we'll start out with the general equation for a single element. We've seen this before. One of our main goals now will be to calculate the equivalent nodal load shown on the right. And in our problem, using our material constants, we're going to get, here is the equivalent nodal load that will tend to expand the element that's been heated, and it turns out to be 100,000 newtons. The force on the right element is going to turn out to be 150,000 newtons, tending to compress the element. Equivalent nodal loads do assemble in the same way that external forces do. In fact, they play the role of an external force in this problem. When we set up our two separate equations for the two elements, we have these disjoint equations, and we already have studied how to handle the mechanical loads here, and so we'll just handle the equivalent nodal loads the same way. And when they're assembled, you see that there is some additive effect at the center node here, so you end up with 250,000 newtons to the right at the center node, 100,000 to the left at the left node, and here actually 150,000 to the left at the right node. I'll sketch those when we get to that figure in the next slide. Well, in this case, because our mixed boundary value problem has constrained the displacements at the two ends, and we don't know the reactions there, but we have no live loads at the center node, we then can uncouple that second equation and solve for the displacement, and we get 0.125 millimeters, which is to the right, and that confirms our initial guess that the center node should move to the right. I'll sketch the loads on this next figure. The displacement is already shown to the right, and then the thermal loads, you see, we're acting to the left at the left end, and then quite an enormous load here at the center to the right, and then the thermal load to the left there. And you can see that that's going to put the left member in tension and the right member in compression. Now, at this point, we've solved the typical discrete problem for displacements, and that's the basic problem. But now we'd like to recover the element properties of stress and strain. So we know that equilibrium says that our rod should be at the same stress. Let's check that out. We go into our stress-strain law, and we can calculate the mechanical strain directly from the displacement field, which was 0.125 millimeter over 100 millimeter length. So that's our strain in the left element. Then the thermal strain came about because of the temperature and the expansion coefficient, and has this value. So when you calculate the stress in the left rod, you come up with this value of 25 megapascals. I've also done that calculation for the right rod, and it comes out the same. So you'll just have to take my word on that. And that would be a good side calculation for you to do, because the numbers would be different, you see. Our second problem has to do with a combination of a rod and a beam, and we're going to have both mechanical and thermal loading. The beam extends from wall to wall between two rigid walls, and then there's a rod that's connected to it by pins both at the top and at the bottom. The beam is not segmented. It carries through this pinned region as a continuous beam. We're going to put a live load of 400 newtons downward at the center of the beam rod situation, and then we're going to cool the rod 200 degrees Celsius. The question is, what way does the center of this beam move? Does it go up or down? And we wouldn't have much feeling for that, I think, on the first try, you can look at the stiffnesses of the rod, you can look at the bending stiffness of the beam and try to make a guess, but I think on the first problem you'd have no hope. Our solution has 7 degrees of freedom that are important. Luckily, the ones out around the periphery of the problem are going to be constrained, so they will drop out. Here's a sketch of the degrees of freedom, the 2 rod degrees of freedom at the top, and then there's 6 beam degrees of freedom at the bottom. We're emphasizing just the planar aspects of the problem. We're not worried about out-of-plane bending. And I'm not worried about the axial compression of the beam. There are no loads tending to bring in the axial stiffness, so we won't model that degree of freedom for the beam. We're going to break the beam into the 2 elements and the rod into 1, so we have a 3-element, 7 degree of freedom problem. Now, if I constrain those degrees of freedom at the left wall, at the right wall, and at the top wall, we really only have 2 remaining degrees of freedom, 3 and 4. But by symmetry, degree of freedom 4 is going to vanish. So we really can just concentrate on what happens to that vertical degree of freedom 3 when the system has been assembled. I'll show the assembled matrix in the 7 by 7 form, and I'll just use dots where I don't care what the entries are. We do know that there's a live load of 400 newtons acting downward on degree of freedom 3. We know that we're going to pick up an equivalent nodal load due to the temperature load in the rod that we have to calculate yet. At degree of freedom 3, we're going to get stiffnesses that are due to the lateral bending of both beam elements, and that leads to this 24 EI term. And then we're going to get the axial stiffness of the rod element, and those are additive. All 3 of those effects are additive from the 3 joining elements. And then here's our displacement U3 on the right. So we need to find the equivalent nodal load for the rod. It follows that conventional rule that we showed. The temperature in this case is negative because it's cooled, and we end up with this pair of 200 Newton forces shown on the right. The important one is the vertical 200 Newton force at node 3, which is positive. We'll add that 200 newtons upward in with the 400 newtons downward, which was the mechanical load, to get the final equation of equilibrium, and write it out in scalar form. We have the sum of the stiffnesses, the displacement. Solve for the displacement, and we get 0.45 millimeters downward. And that's to be expected now, because with the mechanical equivalent of the thermal load, we now have a way to say, oh yes, the beam should deflect downward because the thermal load wasn't as big as the mechanical load. Problem 3 is a 2-dimensional problem with a constant strain triangle. This is a plane stress triangle as shown. It has a pin at the left and a roller at the right, and of course using a single element for this example is a little bit presumptuous, because this constant strain triangle will maintain straight sides when it's heated, cooled, pulled, pushed, and that's more appropriate when it's embedded as one of many elements in a total assembly. But for us it's okay, and we'll just treat it as a kind of a degenerate assembly. The element's going to be heated 100 degrees Celsius, and the question is, what is the vertical load at the top node? So we're interested in finding what the force is going through here that reflects the 100-degree heating and would cause similar strain. Now the element's symmetric about the base, and so we wouldn't expect a horizontal force at that node. The model itself is made of aluminum 10 millimeters thick, so it's really a plate. It's pretty husky, and we're going to expect pretty high thermal loads here to stretch it. The materials are just the common aluminum material properties. The shape function matrix for the triangle is also given as a part of the problem statement. It's here, and I have figured out the components by looking at the equations for the inclined lines and so on. Now in our solution, we use the standard formula for equivalent nodal loads due to a thermal load, and originally it's a volumetric integral. In our case, we're going to put it into a summation form because we think we can get by with fewer calculations than one normally would. In particular, we only want the component F6. In other words, the vertical load on that vertex at the top. This means that in the summation form, if were this Fi and the B were B would have been Bji, then the 6 occurs in this location. That's a little tricky, and I find that the transposition is a lot more tricky operation than people think. The reason is we're trying to locate terms back in the original form of the matrix, not in the transposed form. And so if the matrix B is characterized by rows I and columns J, and then if we transpose it, we reverse those roles. But I'm interested in the original form, and so when we come up with the Bj6, it means we're looking at the 6th column in the original matrix form. Then we have the generalized Hooke's law and the strain matrix. Now, because we only need the 6th component of the force, we then see that we only need to look at the 6th component or the 6th column of the B matrix. And that will let us simplify the calculation of the B matrix, which I show here. B is D times N. Now, if I use a summation form, what I'm saying basically is that we have Bi6 equals Di, and let's use a summation J times Nj6. This free index goes with this one, and then there's a sum over J in between. Now what I've written out here then shows the 6th column of the shape function matrix. That's all I'm going to need, and when I do the relevant calculations to get the 6th column of the B matrix, then that's all I need to do. Now the material law is a common plane stress law. The pre-strain term is pretty easy because it's just the strain due to the temperature load. We worked that out before in plane stress, and you only get the strains in the x and y directions here, which are, for us, principal directions of an isotropic material. So it turns out that all the terms in the integral are constants, and the integral itself reduces to an area integral, which is no problem. Then the constants, when written out, have all of these terms in general, but because of zeros in the B matrix, we knock out some pretty big terms here, and then because of a zero in the G matrix, which is the generalized Hooke's law, we knock this out, and we really come down to only 2 terms contributing. I'll write that last equation out using the symbols involved. So we bring in our temperature effect and our material properties. I'm showing the area here. Now the area is simply AB because A is the half base, and so I can make that replacement, which then allows the cancellation of the B's. The material terms I can gather together, and I get a cancellation of some of the Poisson ratio terms. Then by putting in the proper material and geometric constants, I come up with this equivalent nodal load due to that temperature in the triangle at the tip here in the vertical direction. And it's a positive load trying to stretch the triangle. So what we've done is taken a heated triangle on the left here and replaced it with a triangle that has the mechanical loads shown on the right. We didn't calculate the reaction forces at the base, but you can get a sense of the magnitude, that it takes rather strong mechanical loads to strain a plate that's a pretty husky plate as much as this temperature change of 100 degrees would require.